Hello everyone, I am Irum and today I will talk about our work evaluation of cinematic volume rendering open source and commercial solutions for the exploration of congenital heart data. This work was done with the collaboration of Israel Valverde and Abdel Moustafa. Congenital heart disease is a common birth defect affecting about 0.8% to 1.2% of babies worldwide. To improve the medical decisions, clinicians need a deep understanding of cardiac structures. Traditional visualization methods such as volume rendering technique, which rely on basic lighting models, prone to image distortion. On the other hand, cinematic rendering, a three-dimensional visualization technique based on physically based rendering methods, incorporate shadows and scattering, can create volumetric images with high fidelity. Healthcare centers have access to a range of commercial and license limited solutions like Singo via Vitria Global Illumination and Mavis Lab to render data cinematically. However, the cost associated with these tools can be a barrier for smaller institutions and individual researchers. On the other hand, open source solutions are both affordable and flexible. Despite this, there is a lack of research comparing different solutions in cardiac applications to identify the strengths and weaknesses of open source software tools as compared to commercial solutions. In this project, we employed a free version of a Mavis Lab to create a pipeline for cinematic rendering. Cinematic rendering involves various parameters that affects visualization results, led us to conduct a thorough assessment of several key parameters. Additionally, we evaluated the performance of our open source rendering pipeline by comparing it with the commercial solution commonly used in clinical settings. This evaluation was conducted using a questionnaire filled out by cardiology experts. We included clinical data from three congenital heart disease patients who had CT imaging for diagnosis or treatment, along with the CT data from two normal adult hearts. Here is a brief summary of the patient data we used in this work. So here comes the cinematic rendering pipeline. The pipeline utilized a visual programming approach, which involved combining different modules. The initial stage of rendering process consisted of loading patient data, typically presented as a series of slices. Following the preprocessing stage, the subsequent step is creating a transfer function. This function maps a voxel value to visual properties like color and opacity. Once the data was mapped to transfer function, lighting and shading were applied to the volume using a physically based rendering workflow. PBR uses mathematical models called bidirectional reflectance distribution functions to describe how light interacts with surfaces based on their physical properties. We selected principal material from Mavis Lab material module and adjusted properties like color, metalness, roughness, and specular to achieve realistic rendering. For the lighting, we used area and background lights. For realistic 3D scene lighting, the intensity, color, and position of both lights were carefully adjusted to create the desired lighting. After adjusting color, material, and lighting, we employ the soap path tracer module for rendering. This module uses Monte Carlo path tracing to simulate light transport, resulting in photorealistic images. It solves the complex rendering equation by considering scene properties and light material interactions. We also used post-processing tools like volume cutting and clip planes for image editing. Once the rendering pipeline is designed to determine which parameters should be adjusted and which values achieved the most realistic appearance, a sensitivity analysis was performed. We tested different base colors for varying brightness and adjusted roughness along with metallic and specular values. Clinicians viewed these images and selected preferences based on the anatomical structure they were interested in. For example, they preferred a matte appearance for the atria and a glossy texture for coronary arteries. We also analyzed different lighting scenarios. For example, having two light sources in the same spot caused blurry reflection overexposure compared to a single light source that focused on image details. We also examined area and background lighting using only area lighting led us to a dark image. while background white lighting alone created a diffuse, natural look. Combining both produced dynamic effects, emphasizing volume features with area light and adding depth and dimensionality with background light. We also employed image-based lighting, which uses high dynamic range images as light sources. In PBR, background light comes from the scene's surroundings. Two area light sources in the first image at the right side of the slide in the first image offer focused illumination, while image-based lighting with HDRI high dynamic range imaging creates realistic immersive lighting by capturing reflections from surroundings. After finding the best settings, we rendered CT images in both Mavis Lab and Siemens Singovia platform. We assessed the results through subjective ratings of photorealistic static snapshots, focusing on anatomical structures like arteria, ventricles, great arteries, and coronary arteries. Ratings were given on the Likert scale from 1 to 5, with 5 questions per case about these specific visual attributes like definition of structure, depth perception, texture appearance, fidelity, and diagnostic ability. So here are the results. The figure shows the standard volume and cinematic rendering of all 5 cases. The top row displays the volume rendering, while the middle and bottom rows show cinematic renderings from the commercial solution and the open source framework. Cases 2 and 3 highlight the significance of cinematic renderings when compared to volume rendering. In addition to visuals, the table summarizes our evaluation findings by averaging scores for all anatomical structure and characteristics. Results obtained by 3 independent cardiologists were consistent in recognizing an overall superior performance of the commercial solution with slightly high scores on the Likert scale, especially for the definition of structure, texture appearance, and diagnostic ability. However, the open source solution had several visual characteristics with a 4.0 or beyond, being similar to commercial alternative for fidelity and depth perception. Both types of cinematic renderings performed worst for the definition of structures due to the low scores given to coronary arteries. The cardiologists also expressed their satisfaction with the reliability of open source rendering tools and the recommendation to others for advanced rendering purposes. Their overall preferences might be open source tools mainly due to their cost effectiveness. And the future work will be devoted to a more extensive evaluation with more analyzed cases, evaluators, and use software tools, including web-based solutions, making it easier for hospitals to use open source cinematic rendering independently of their resources. Thanks. Thank you for your attention.